So we've covered quite a lot of ground over the last 4 sections of the course, and we ended up with a method that got us to extract the best observable quantities we could extract out of our observations. And now it is time we go about using that data. Now I want to start with a little flashback about something that was covered in the very first unit of this course that described what I think is a good outline of the general cycle of the scientific production, going through 4 phases that started from an initial curiosity that motivated the development of this entire field. How do I get access to the details of the surface of stars, or the details of apparently unresolved objects? That curiosity got us to come up with an observation technique and to design an observing mode that we've called interferometry. That design came up with some consequences in the way to extract the data, because the data is of a very peculiar kind, and forced us to develop some special craft, how to best extract that data. We are now reaching the point where we are finally going to be able to use that data to produce some answers to the questions that first motivated our observations. So we're finally getting on to actually doing something that is about the targets we're observing. We're actually going to do the science. And for interferometry, there are 2 ways you can go about exploiting the data to produce some science. The 2 methods are going to be something that we call interferometric imaging, that is, use the observations and invert them to produce an image. And the other approach is going to be something that we call model fitting, where we throw in some assumptions about the object that we've observed, and we're going to try to constrain some of the parameters of that model. Somehow, these 2 approaches to data interpretation are very related to each other and have to do with deduction of information, of consequences from the data that was observed. And it's all going to be about this art of inference. And it is indeed inference and not a typo of interference that you have here on the screen. You may have heard this statement a couple of times: scientifically proven, usually employed at the end of a commercial for a special beauty product, for example, that is used to dissipate any shadow of a doubt about the validity of the statement that were previously made. This statement, scientifically proven, turns out to be a bit of a fallacy. That may come as a shock, but it's actually fundamentally impossible to prove that anything is true. What is possible is to scientifically prove that something is wrong. And the way you do so is, for example, by producing a counterexample, or by pinpointing a contradiction or something that's going, an absurd consequence to the theory that was at the origin of that statement. And in practice, it is impossible to prove that any theory we have of nature is true. The reason for that reality is that our reasoning is always going to be based on an incomplete set of information. We don't have all of the cards in the game to be able to draw a conclusion that is going to be final. And our conclusions at any time, given the availability of new data, for example, can be revised and lead to a conclusion that is very different from the one we started from. And so the result of our theories ends up being probabilistic in nature. And what is a probability? A probability is going to be some real number between 0 and 1 typically that quantifies the amount of trust we have in a given theory. One way to see that is simply by acknowledging that even measurements are probabilistic. You can, because every measurement is associated some level of uncertainty, in the end, a measurement is some probability density function that is parametric, and the only thing we are really able to produce is a most probable range of values, and that has a finite probability. Let's look at one example in particular. Let's imagine that we'd like to characterize the angular diameter of a star. This is one of the first applications we're actually going to really cover in this course. And let's say that we're going to try and identify this probability or density probability function, which is going to be a function of our parameter theta, the angular diameter of our object. And we hope that we are going to be able to infer some distribution that looks something like that. Now, this probability density function is actually a probability of validity of our hypothesis. And that probability is dependent upon the data that is currently available and any other implicit amount of information that we are using to even unconsciously in a way. For example, we never assume that the luminosity of a star is going to be nothing but positive. We don't expect the luminosity of a star to be negative. And yet that is what we would consider common sense is in a way some implicit information that we throw into our interpretation of the data that is going to have an impact on our interpretation. You have to realize that all of our theories are conditional. And the way you would see this is when we explicitly write that our probability is a conditional probability that is dependent upon information, data, that is going to affect our interpretation of reality. And because this data is conditional, it is strongly dependent on the prior assumptions that we have about the object we are looking at. To illustrate this idea in a somewhat playful manner, let me tell you a little story that is, in a sense, a bit of a cautionary tale of an elephant who's currently asking you, well, how would you go about modeling an elephant? It's actually an old story that is used in a couple different cultures, and many different versions of the same tale exist, but we're going to look at this one in particular that we could call The Elephant and the Wise Men. Now, this is a story happening in some rural area where a couple of men that are enjoying knowledge, very curious about everything, hear that for the first time in their life an elephant is actually going to go through their village, for example with a circus. Now, one particularity of these men is that in addition to being very hungry for knowledge, they also happen to be blind. And therefore are going to experience the reality of what an elephant really is only by their sense of touch. The story is interesting because each of them actually approaches the elephant from a different angle. The first one reaches for a given direction and happens to stumble upon the ear of the elephant, and after touching it a little bit, finally concludes that the elephant this wanderer is heard about is very much like a fan. Makes a pretty reasonable conclusion, from the observation that were at his disposal, given the prior knowledge he had of things like fans. Now, the second guy comes from a different angle and happens to reach for the leg first thing, and rapidly concludes that the elephant is nothing but a pillar. Different conclusion, different observation, different conclusion. And the story goes and goes. A third one reaching for the tail concludes that the elephant is very much like a rope. And finally, a fourth one happens to first touch the tusks of the elephant and naturally concludes that the elephant is very much like a spear. Now, all of these guys are unlucky in a way. In addition to being blind, they just have very partial information about a very complex reality. And their prior assumptions really drives their conclusion in a very drastic manner. And here I'm going to read from an actual poem that is inspired from the original story by John Godfrey Sachs, something written at the end of the 19th century. It's called The Blind Man and the Elephant. I'll put the text following up on this video, but this is the conclusion of their tale. And so these men of Indostan, that's the name of the area where these guys are from, disputed loud and long, each in his opinion exceeding stiff and strong. Though each was partly in the right, all were in the wrong. Now, this is a tale, of course, and the reality is not as caricatural as this story, but nevertheless, this is a word of caution. We are going to have to be very careful when the time comes to interpret our data, to not throw too much assumption into the data, because our deductions could very much lead us astray.